White dwarfs. White dwarfs are the final stage for stars that began with a mass somewhere between 0.25 and 12 solar masses. That is 0.25 to 12 times the mass of our Sun. So this is the fate of low-mass stars. So as we can see here, the MKGF stars and the lower end of the A stars will all end up as a white dwarf. Now recall with these stars that we left them with a red giant that had a carbon and oxygen core that was inert, that is, it was not generating energy, and there was a helium fusion shell and a hydrogen fusion shell. And the helium flash had blasted off the outer layers, and it had exposed that carbon and oxygen core. Well, since it's inert, it's going to be collapsing down. And it turns out that the mass of that core is going to be less than 1.4 times the mass of our Sun, depending upon the mass of the original star. But anywhere from a very small fraction of the mass of our Sun up to 1.4 times the mass of our Sun is what's left in that core, and it is collapsing down since there's no energy being produced. What stops the collapse is what's called electron degeneracy pressure, which sounds interesting. It's essentially electrons pushing against each other, because all electrons have a negative charge, and like charges repel. So if we take our normal matter, where there's mostly empty space, and we compress it down to the point that the electrons are next to each other, their orbits aren't separate between the atoms, then that is going to put it into what's called a degenerate state. And degenerate basically means that you're going to start to violate some of the laws of physics under normal circumstances, because electrons aren't supposed to be in the same place with the same energy at the same time. So we're getting dangerously close to violating that. So this electrical repulsion stops the collapse. Now we have a force pushing out. The electrons pushing against each other is going to be an outward force, and then of course gravity is an inward force. And so the combination of these two reach a balance point, and the collapse stops. That core is going to be small, as you can see here, about the size of the Earth. So we have 1.4 solar masses, all compressed down to almost the same size as the Earth. So this is going to be very dense. If you had 1 teaspoonful of white dwarf matter, it would weigh roughly 10 tons. So that gives you an idea of how insanely packed together this is. Also recall that a white dwarf is made of carbon. Well, carbon under pressure is a diamond. So a white dwarf is essentially an Earth-sized diamond, but with an insanely high density. Because they're small, white dwarfs are quite dim. So it's rare to see one. We do see the white dwarf in the Ring Nebula. That's one of the few that we can see in photographs. But for the most part, white dwarfs are, by and large, too faint to see. They're also going to be incredibly hot, 21,000 degrees Fahrenheit. Original temperature was about 100 million degrees Kelvin, which was the temperature needed for helium fusion. Well, now that it's exposed, it's cooled off, but it's still very, very hot. So in terms of the HR diagram, recall that our vertical scale goes from dim to bright, and our horizontal scale goes from hot to cool. So hot and dim, there's the white dwarfs. So the white dwarfs are always going to be in this lower left corner of the HR diagram. This guy is Subramanyar. I don't know if I'm going to spell this right or not. Subramanyar. Close. Chandrasekhar. And it was actually on a boat trip from India to England to begin graduate school at Cambridge University that he sat down and did some calculations concerning white dwarfs. And what he found was, if a white dwarf exceeded that mass of 1.4 solar masses, then electron degeneracy pressure was not strong enough to stop the collapse. Degeneracy. And so if it's too massive, the white dwarf collapses to zero size. So we now call that mass the Chandrasekhar limit. So this, a white dwarf can't have a mass over 1.4 solar masses is the Chandrasekhar limit. Now it turns out that there is an intermediate possibility besides collapsing down to zero size. But as far as it being a white dwarf, 1.4 solar masses is the maximum a white dwarf can be. Now over time, a white dwarf cools off. It's not generating any energy. So it's really just this hot hunk of diamond out in space. So it does cool off over time. And when it has cooled off completely, we call that a black dwarf because it no longer gives off light. Now, no white dwarf has existed long enough to cool off to the point of being a true black dwarf, but this is the final stellar corpse of a low-mass star. So this is going to happen to our sun. It won't start going through the giant stages until another 4.5 billion years or so. So don't get too concerned. But ultimately, our sun is going to end up as a black dwarf, as what happens to all low-mass stars.